In this video, we're going to be talking about some very useful transformations for our time series. That the usefulness of these transformations comes from the fact that we are able to extract simpler patterns that exist in a time series that we can exploit to produce good forecasts. So the idea here is that we want to remove any type of known variation that we are seeing in the time series, uh, or any type of random variation that exists in the time series. We'll see what this means shortly. The idea behind doing any type of transformation is to stabilize the variance across time. So you're familiar with the word with the phrase covariant stationary time series. We've talked about that. Now we want to try to stabilize the variance of a time series, and this is useful again because it helps us forecast. But the reason why we do it is because if we look at our data, sometimes the data would show a different level of variation at different levels of the series. So here, let's try to, before we try to see that in a graph, we can try to understand what we're going to be doing. So we are going to have some original observations denoted by y, so y1 through yn or yt, and then we're going to use some kind of a transformation on that, and we're going to call that w1 w, which is the time series, which is the transformed time series. Okay, now it might be useful for you to try and read some of the sections on different types of adjustments and transformations that we can do with time series. One type of adjustment is called a calendar adjustment, in which we try to remove the seasonality that exists in a time series. So any type of pattern that we see within the year, we try to remove that, and that is also known as seasonal adjustment. So if we're not so focused on making seasonal forecasts, then and we're just focused on maybe year-on-year forecasts, then we can try to do a calendar adjustment for the time series. So we want to basically remove the seasonal variation that exists in a time series. Sometimes it's useful to look at macro variables like unemployment rate, etc., and try to remove the seasonal variation from it. The other type of adjustment or transformation is called population adjustment. So sometimes when you're looking at the GDP of a country, that can be heavily influenced by the size of its population. So you want to always look at GDP per capita or GDP per population. So those are population adjustments. We also might want to adjust our series for any changes in inflation over time, which is the general increase in the level of prices. Again, a lot of macro variables like GDP, consumption, investment, they are adjusted for inflation. So we're actually able to see the real value of that series. What we're going to be focusing on is called a mathematical transformation. But all of these types of adjustments are trying to do the same thing. They're simplifying patterns in the data by removing any type of variation that we already know. All of this is again done to produce more accurate forecasts. Now, the different type of mathematical transformations that are used for stabilizing the variation in time series are of two types. One are called power transformations. So where your transformed series Wt is equal to your original series Yt raised to the power of p, where p is the power of the time series. So one example is if you take the square root of a series where p is one half, and cube root is another type of example of a power transformation where p is a third. Logs are also very useful and are used a lot in economic data. where the transform series is just the log of the original series. Now, logs in particular are useful because they are, or they help in the interpretation of data. So if you take log of yt minus log of yt minus 1, which is the change in the log value from one period or between two periods, that change can be interpreted as the relative or percent change on the original scale, which is very useful for us. And typically, logs also help in reducing the variability of a time series in general. So let's try to take a look at this particular series, which is, again, if you want to reproduce this chart, you can follow this code here, where we're looking at Australian retail data and filtering that by industry and focusing on the food retail industry and looking at the turnover. So what we're plotting here is the turnover in that sector in Australian dollars over time. And what you can see here is that there is an increasing trend in this time series. But we can also see that as we move across time, the level of the seasonality, right? These peaks and troughs that you see, the difference between the peak and the trough has increased in size right here relative to right here. Okay, so there is this change in variation that we see across the time series. What we want to do is we want to keep the variation quite similar across the time series, and there are ways we can do that. So let's try to look at what happens if we take the square root of that series. So now here we are plotting the square root of the series. You see that the difference between the peaks and the troughs, are not as different as they were previously, right here. Okay, so again, this is the square root series, and this is the original series. So we see that as we are taking the square root, this is these variations that we see are trying to be equalized across time. Now, we can also see the cube root, okay? So here is the cube root of that series. And this is again interesting because it does change or morph the series in a different way. We can also take a look at the log values of the turnover series, which is our original series. Of course, turnover is positive, so log values, in this case, all our values were positive, so we don't have a problem in taking logs, but you should remember that whenever you are taking logs, you can't use logs for series that have zeros or negative values in them. Okay, that's not going to be, it's not defined for that, those particular values. Okay, so you want to be careful of that. But there are ways around it. Sometimes people add constants and try to make the series positive. Okay, this is another type of transformation for the turnover series where we are looking at the inverse of the series. And what this does is it basically, in the initial periods, because it's the inverse, it's raising or increasing the variability in this part here and reducing the variability here. So this is also what we don't want. We want the difference between the peaks and the troughs to sort of stabilize over time, even if there is a trend. So this brings us to what we call BoxCox transformations, where each of these transformations belongs to whatever we have discussed so far, the log transformation and the power transformation. Each of these transformations is close to a member of the family of the BoxCox transformations. This is heavily used in statistics, and the name BoxCox comes from the authors, Box and Cox, who wrote a seminal paper in 1964 that was called An Analysis of Transformations. And it was published in a very good journal called the Journal of the Royal Statistical Society. So the BoxCox transformations depend on a parameter lambda. Now, the transform series here, which is WT, would equal the log of the original series if lambda is equal to 0. Okay. So the BoxCox transformation is conditional on the value of lambda to make the series continuous. Okay. And WT is going to be equal to some sort of a power transformation if lambda is not equal to 0. Okay. Now, if lambda is equal to 1, let's think about what happens. If lambda is equal to 1, then we're obviously thinking about yt to the lambda minus 1 over lambda. So wt will just become yt minus 1. So if lambda is 1, we're pretty much looking at no change in the shape of the series, and the series is just shifted downwards with a magnitude of 1. But for all other values of lambda, the series will significantly or not so significantly change its shape. The goal is to find the optimal value of lambda that makes the size of the seasonal variations, which is the difference that we see between those peaks and troughs, if you were eyeballing, the same across the time series. So we would then say, if we could find that value of lambda, then we have stabilized the variance. Okay, so this is just summarizing the same things again. And let's try to illustrate this point by looking at what happens if we change the value of lambda in this type of a time series. So here you have the same turnover series. So we have the original series as we were seeing it, where the variations are less here, variations are huge here, the seasonal variations, and we are looking at a value of lambda equal to 1, where the series is sort of the same as it was on the original scale. What we're going to do is here, you're going to see different values of lambda, and I'm going to play a video and you're going to be able to see how the series gets transformed. So I'm going to play it one time and we'll discuss. The value of lambda is decreasing, and notice how the seasonal variation across time is changing. So here we see the series is transformed for a value of lambda equal to 0.01. So if we went back to this is our original series, right? This is very different than where we end up. So the value of lambda can change the series, and we can figure out what's the optimal value of lambda. So it seems like if the value of lambda is close to 0, this is actually making the size of the seasonal variations the same across time. Okay, so we might be better off. But how do we find that? Now, R is going to do that job for us, and you can read some of these things on your own, but really the idea here is if lambda is close to 0, then the series is just going to look like the log of the series. And there are some other points that are just inferences from what the transformations can do. Now, how do we get to the optimal value of lambda? So what you can do is you can start with the food series, and you can head food to see what it contains. Now, you can use the pipe function on it and use the features function on turnover, which we had created before, and say features equals Guerrero as the argument. Okay, now Guerrero is an argument. Well, you You just have to remember that this is what you need to do if you're trying to find the value of optimal value of lambda. This argument is based after the author who suggested this. So in our case, if we run this command, we get a value of lambda which is close to 0, 0.05. So it's saying that when lambda is 0.05, the turnover series would be transformed in a way that stabilizes its variance across time. So in other words, if the value is close to 0, this is as good as a log transformation. So we'll see what we're able to do with that. Now, you might be interested in, once we've transformed the series and we forecasted our time series, we might want to back transform the series to its original value, because that's what we're concerned with. So those transformations are done by using back transformations in such a way. So if you had logs, then the exponent, if you take the exponent of the transformed series, that would convert the series back to its original value, and so on and so forth. So we can take a look at how do we model our time series using these transformations, now that we know that our turnover series should or is need to be transformed in a way where the log transformation is the best transformation and it stabilizes the variance across time. We can assign fit to this operation that we're doing here. So we'll take the food data and use the pipe function on it, use model, and because we see some seasonality in it, maybe the seasonal naive function model is the best one. And we're going to say take the log of the turnover. So we're not using turnover, but the log of the turnover, and we are specifying, what the lag is. It's a year. So what we get when we specify the model is called a Mabel. So a Mabel is just a model table like we had defined before. And we just have one model here, which is our seasonal naive model. We can then create our forecasts. So we can use the model S-naive, which is contained in fit, to produce a forecast using the forecast command. And H here is our forecast horizon. So we can say H equals 3 years, or H equals 36. Okay, so H equals 36 or 3 years would give you the same thing. You will end up with a fable, which is a forecast table with 36 values of the turnover data. Okay, and here you have 36 values because that's 3 times 12, because this is monthly data, right? Notice the months are specified here: January, February, and so on and so forth. Okay, and you are given 4 different columns here. The first column being dot model, which is just one model here. The second is giving you the month, which is the time index. And then you have turnover, which is the forecasted value of the series. And then you have the dot distribution column, which gives you the estimated probability distributions of your forecast. So we can plot the forecast, okay? We can plot the forecast using the variable that we created here, FC, which contains our forecast, and using the autoplot function on food. So we can try to restrict, I mean, you don't have to do this, but here the restriction is that we're going to focus on the more recent data. And so we produced forecast out into the future. And if you don't give the level equals null command, then this is going to produce 80 to 95% confidence bands around these forecasts. Now you can also try to do the same thing for gas production if you wanted to try. There is also something known as bias adjustment that is done for the time series. Bias adjustments are issues that arise, or biases are issues that arise when we are dealing with median forecasts versus the mean forecast. Really, the issue is with the median forecasts. So, what happens is that when you're doing these mathematical transformations like BoxCox transformations, the back transformed point forecast is typically the median of the distribution and not the mean. But a lot of times we are concerned with averages or means of um, any type of time series. Okay, we are interested in averages. So sometimes we could get into this problem of medians not adding up for a particular region or for a set of countries, but means do when we try to back transform. So we might want to look at some kind of bias adjustment for that. And it's very easy to do that in R. Now here's a little bit of math. You don't have to worry about that because this is an applied class, but the back transformation is given by f of x, okay? And that's just a Taylor series expansion about its mean. So whenever we are using the mean rather than the median, the point forecasts are bias adjusted. So we want to do that. And here's a little snippet of the code that would help you understand it. There's a nice diagram in your textbook that talks about how you can do it. So the only thing you want to do is, only thing you want to remember is that if you're using the forecast command and you're forecasting ahead, this type of a forecast is already bias adjusted. But if you want a biased forecast, which is if you want to focus on the median instead of the mean, then you have to give this option of bias underscore adjust equals false. Okay, but this is getting into more details around it. So you can take a look at that in your textbook.